Okay, so here's the problem I want to work out. It's from the book. I'm really sorry about my poor filming skills and inability to focus sometimes on things. I hope this is working out. Anyway, let's get a better picture there. So, it is known that nationally, doctors working for health maintenance organizations, aka HMOs, average 13 and a half years of experience in their specialties, with a standard deviation of 7.6 years. The executive director of an HMO in a Western state is interested in determining whether or not the doctors at this HMO have less experience than the national average. A random sample of 150 doctors from HMOs show a mean of only 10.9 years of experience. So the question is to state the research and null hypothesis, test whether or not doctors in this Western HMO have less experience than the national average, and then use an alpha level of 0.01 and perform the test. This is very typical of what you'll see. So again, you see that I give you the alpha. I'm giving you all these, obviously all the, data points. And I'm also, one thing you want to see is I'm specifying whether I want a one or two-tailed test. So you can see that I want to determine whether or not doctors have less experience than the national average. So that would be a one-tailed test because I'm assuming the directionality. If it were two-tailed, I would just say it's not equal. Again, that's usually specified for you. Okay, so let me go over here and work this out. So the first thing you'll want to do is always state your research and null hypothesis. And I think it might be best to always put the null first and research. It doesn't really matter, but I don't know, it keeps me organized. It makes more sense for me to see H sub 0 and then H sub 1. Okay, so your null hypothesis is always going to be this. It will always be mu equals some number. So in this case, that mu is equal to 13 and a half years. Remember that on average, HMO doctors have 13 and a half years of experience in their fields. But what we found was that in this sample of this HMO out west or whatever, so we're looking at this one HMO, and found that it has doctors, the doctors of this HMO had 10.5 years. So the temptation for you might be to put something like equals 10.9. You'll always have the exact same value that you're testing between the null and the research. So in this case, if the null, that it's equal 13 and a half years, the research would be that it's less than 13 and a half years. And you can think of it big picture-wise what you're doing. You're basically testing to see, is this number significantly different than 13 and a half? Or could it be driven by sampling error or general small deviations in general? I mean, think back to the estimation. We always, when we're estimating something, we always get a point, but we're always bounding it with a confidence interval. So it's almost like, if 13 is what 13 is the mean, given the sample mean of 13, if we continue, think back to the central limit theorem, we continue to draw samples of a size, say 50, over and over and over again, and we got a sampling distribution of the means, could we reasonably expect to get a sample which has an average of 10 and a half or 10.9 years? So your research hypothesis is going to be that the population mean is actually less than 13 and a half years. Okay? So here's part one, and I kind of skipped over. Obviously, I'm not going to do this to you just because I'm not. I mean, I don't think anybody needs any tricks in their life right now. But the first thing you want to make sure is this randomly sampled? Well, yes, it is. It says a random sample of 150 doctors. Is it an interval ratio variable? Yes, years is in interval ratio form. So make sure you're kind of checking off those assumptions. Don't overlook those. Obviously, if it's not a random sample, that's the end of it. You can't do any of this. Okay, so go back to our 5 steps. We make the assumption, we state the research and null hypothesis, and select alpha. Alpha was specified for you as, let's see, what was it? 0.01. So, whoops. So we have an alpha. And my pencil's out of lead. All right, there we go. Jeez. Alpha equals 0.01. Okay. So the next thing we need to do is select the sampling distribution and specify the test statistic. We can use Z in this case because we know the, sorry, where was I? Because we know the standard deviation for the population. So the key here is that we know the population standard deviation. So if you want to make a note of things, this first test is comparing a sample to a population when we know the standard deviation of the population. So if we know that, then we can use Z. And if you think back to your, let me click back here just so you can see the equation, okay? So Z is equal to the sample mean minus the population mean divided by the population standard deviation, gosh, it's a mouthful, divided by the square root of the sample size, okay? So if we go back here, we have Z equals sample mean minus population mean divided by the population standard deviation divided by the square root of n, okay? So we already have these numbers, so this is really just kind of plug and go from now. So what's our sample mean? Well, that's the 10.9 years. Right? What's the population mean? 13.5. What's the population standard deviation? 7.6 divided by the square root of 150. Okay. I've already worked out the math on this. Negative 2.6 would be your numerator. Your denominator is going to be 0.62. Sorry about flipping the video around. Here, let's just keep it upright just so you can, I don't want you turning your heads. So, negative 2.6 and then 7.6 divided by root 150 is going to give you 0.62. When you calculate that, you're going to get negative 4.19. And that's your Z statistic. That's your test statistic, right? So what do we do now? We've got the Z. This is the part that's not new. Flip back to the table. Use the standard normal table. And you've got a Z equal negative 0.419. And Z only goes up to 0.4. So we can assume here that we have a p-value equal to 0.0001. It's actually less than that number, but it's not going to make a huge difference for our one-tailed test. And we said that alpha was equal to 0.01. So if p is less than alpha, we reject the null. If p is greater than alpha, we fail to reject the null. In this case, p is less than alpha, so we reject the null hypothesis. And the conclusion, and this is maybe, don't overlook this part, it's probably the most important. So you reject the null hypothesis that this Western GMO doctors have the same experience as the national average. So your conclusion would be that this GMO, good grief, HMO, thinking about food. This HMO has, the doctors at this HMO have less experience than the doctors do nationally. Okay, so your conclusion would be that the basic idea is that 10.9 years of experience is significantly less than 13.5 years of experience. So how would you write that up in a sentence? Well, the HMO doctors in that Western HMO or whatever, but the test HMO that we looked at has less experience than the average HMO doctor. So this might not be the place you'd want to go to, I guess. But that's kind of it. One last thing on that is because we're using sample data, we never really know whether the null hypothesis is true or false. So there's always a degree of uncertainty. So we can say we're 95% confident, in this result. So in this case, we could say, so we did an alpha of 0.01. So in our case, we're 99% confident that this Western GMO has less, less experience among their doctors than the national average. So, we're 99% confident. Obviously, that means, the flip side of that is that we're 1% not confident. So a type 1 error is the probability associated with rejecting a null hypothesis when in fact the null is true. So our decision here that we're 99% confident that this Western HMO has less doctor experience than the national average. Well, we're opening ourselves up to potentially having a type 1 error. There's a lot more that we could do with this. I'm going to kind of leave it at that just because I think there's other things that we could spend our time on that are, a little, I guess a little more important, for lack of a better word. But just in general, some people study this a lot and looking at how can we reduce type 1 and type 2 errors. Now, obviously a type 2 error is when we fail to reject the null, but the hypothesis is false. So if we found that there is no difference, but in fact there really was, that would be a type 2 error. Obviously, they're inversely related, so as your susceptibility of type 1 error goes up, your susceptibility to type 2 goes down, and vice versa. But don't get too hung up on that. Just know that in general, there are these, we have different types of errors that are possible with this estimation. Because like I said, we're 99% confident, but that means that there is still a degree of uncertainty. That's kind of the blessing and the curse of inferential statistics, is that while it tells us a lot, there's no such thing as 100% confidence in anything. We can increase our confidence level, but we'll never be 100% sure, but such is life, I guess. You're never really 100% sure of anything. Okay, so that's the first nugget of 4 within hypothesis testing. And you can see now why I only want to do 2 today, and I'm going to do 2 tomorrow. But this is in cases where we're taking a sample statistic and comparing it to a population parameter when we know the population standard deviation. So again, that's kind of the key. Comparing a sample statistic to a known population parameter where we know the standard deviation of the population. Okay, so that is the first bit. Second bit, I'm going to pause the video and come back with the second.